Hello, and thanks for using TechBoom. In this video, I'm taking a look at a question that was posted on the Board of Studies forum in the Extension 1 section. So it's a volume of revolution question, and typically there's two techniques you can use to work out volumes of revolution, what I'll call slices, and another method called cylindrical shells. Now, typically you'll learn about slices in Extension 1 and cylindrical shells in Extension 2. And even though both techniques can get you the answer that you'll be looking for in terms of calculating the volume, because this question was asked in a forum in relation to Extension 1, I'm going to restrict myself to using the slices method. And in any case, I think that's the method that you'd probably go with for this question. So the question has two parts. Part A says to find the area enclosed between the curve y equals 1 on root 1 minus x squared, the x-axis, and the lines x equals 0 and x equals a half. So the student didn't have any issue with that. That's the kind of typical kind of calculus, find the area beneath the curve kind of question. Part B is where the student was seeking a bit of help. So part B says the corresponding area enclosed between the curve and the y-axis is rotated about the y-axis. Find the exact volume of the solid formed. So that's what I'm going to work through now. So I guess the first thing worth noting is the curve that we're concerned with. So that's y is equal to 1 on the square root of 1 minus x squared. And I think with any volume of revolution question, a natural place to start is to sketch up what you're dealing with, because these kind of volumes formed through revolution, it's such a kind of visual thing that you need to get your head across, that trying to draw it up should help you at least a little bit. So I'm going to just sketch up an axis quickly here. That should do. So we'll have our x-axis, our y-axis, this is the origin, and we're kind of told that we're concerned between, well, we've got a line of x equals 0, which is basically the y-axis, and then we've got the line x equals a half, so I might just put this as a half, and maybe in a different color I'll just draw that line of x is equal to a half, which is a vertical line intersecting the x-axis at a half. So that's x is equal to a half. And then finally the curve here that we're concerned with. And then we want to see how this curve, however it looks, and the y-axis, x is equal to half, and the x-axis, whatever that area is, we want to rotate it around. So step one will be to sketch up this curve as well. I might just kind of mark out my y-axis here. So maybe if I call that a half, so that'll be 0.5, we'll call that 1, and that would be 1.5. So let's just kind of get some key points. For this curve here, when x is equal to 0, y would be equal to 1 on the square root of 1 minus 0 squared, which hopefully you can see would just be 1 on the square root of 1, or just 1. So when x is equal to 0, y will be 1 for this curve. Let's have a look at when x is equal to a half. So when x is equal to a half, y would be 1 on the square root of 1 minus a half squared, and maybe I'll just write that as a half, the fraction, because we can kind of simplify that as 1 on the square root of 1 minus 1 on 4, and so that's 1 on the square root of 3 on 4, and then I might just keep going this way just because I'm running out of space. So that is going to be 1 on root 3 on 2, which I can just write as 2 on root 3. So if I just get my calculator and kind of plug that in, 2 divided by the square root of 3 is about 1.15. So 1, that's 1.25, so it's going to kind of be under there. I'll just kind of plot it about here. So that's 2 on root 3. And what we'll see is that it's basically going to follow this kind of shape between those 2 points. You could plot some more if you want, but hopefully it's not too hard to see that that's the basic shape. So in part A of this question, the student would have been finding this area here, the area that's between the curve, x is equal to 0, x is equal to a half, and the x-axis. So now it's this area that we want to rotate around the y-axis to form a volume. And personally, when I was first learning this, I always found it a bit hard to visualize, but I guess as you work through these questions enough, you start to get a bit more comfortable with picturing what that looks like to rotate something around and kind of see how it converts into a three-dimensional object. So what we're going to do is we're going to now work out that volume, but I guess the benefit of drawing up this curve is we can start to kind of see visually what are we really dealing with. And actually, to get this specific area here rotated around the axis, we're actually going to do that in 2 steps. Step 1 is we would rotate this vertical at x is equal to a half around the y-axis. So this bit here, just between 0 and this intercept 2 on root 3, just that line there, we'd rotate around, and that would form a cylinder. And then this part here, so kind of if I just kind of dot along there, this part here, we'd rotate that around to form another volume between y is equal to 1 and 2 on root 3. We'd rotate that around, and taking the first rotation minus this rotation would leave us with this shaded area rotated around. So we need to do it in 2 steps, and I think that would be very hard to realize if you didn't first draw up the curve. And so now what I'll do is I'll work through I guess basically the technique of slices for each of these steps, because if we think about the 2 bits, maybe I'll use black for this line here. Basically what we do is for all the values of y between 0 and 2 on root 3, we kind of draw a very thin slice, as thin as possible. And we'd rotate that slice around, and we'd work out what's the volume of that slice. And then we kind of add them up for all the values of y that we're concerned with. And if we think about what would happen if we rotated this around, if I just kind of draw it off to the side, we'd essentially get what I like to think of as a coin. It kind of looks like a coin if you kind of think about it looking from a bird's eye view, where the coin's height is essentially this thickness here, which we typically call dy, because it's just some movement in y, and as we get to integration, we'll kind of get to that concept where we want to find the limiting sum as that change in y gets smaller and smaller, which kind of is the essence of integration. And then basically this is, being a coin, it's essentially a very thin cylinder. And so if we can work out the volume of this thin cylinder and then add it up for all the y's that we care about, we'll get the total volume of this whole line. And so here the volume is going to be the area of this face times the height. Now the face here is a circle. The area of a circle we know is pi r squared. here, if we're rotating it all the way around, the radius would just be this first half, which is our x value of a half. So the volume would be pi times a half squared dy. So that's the volume of an individual slice, and then we're going to basically add up all of the slices, and that's how we'll get to integration, which I'll write out the integral. I'll probably have to turn over when we get to our integrating. But before I do, maybe in a different color, let's now think about only the slices that we care about if we're rotating this curve around the axis, so kind of this area here. So we'd have a slice that would just go up to the curve. And same kind of idea, if I just draw off to the side, we'd also get another coin, again with the thickness of dy, but this time the radius of the circle that gets generated, it's going to be different each time depending on what y value we're at. And the way we can simply write it is that the volume is going to be pi times whatever the x value happens to be for each slice. So I'll just write that as x, that's the radius, squared, because the area is pi r squared, and once again times dy. And I should note that for rotating this line at x equals a half around, the y values we care about go all the way from y equals 0 all the way up to y equals 2 on root 3. So that'll be the boundaries of our integral. For this bit here, these red slices, the integral will just go between y is equal to 1 and y is equal to 2 on root 3, because they're the only y values that we care about. So what I might do is I might just turn over at this point, and let's just write up our integrals, and then it just becomes a problem of integration. So our volume is going to be equal to the integral, which is just a fancy way of doing a sum. This is kind of, you can think of this as like a stretched out s for sum. The integral between 0 and 2 on root 3, there are y values, 0 and 2 on root 3 of all of these slices. So pi times a half squared, which is a quarter. So essentially pi on 4 dy. So pi on 4 dy. So remember, that's going to give us all of this rotated. So then we subtract this bit. So that we'll then get a minus of another integral. And as I mentioned, this will only be between 1 and 2 on root 3. So between 1 and 2 on root 3. And the slices that we care about here is pi x squared dy. Pi x squared dy. So now if we can solve these two integrals and evaluate them between our boundaries, we will get our volume. Now notice that in this first integral, pi on 4 is just a constant, so we can bring that out, and then we're essentially integrating 1 with respect to y, which is easy enough to do. For this second integral, the pi, yes, we can bring out as a constant, but the x squared, if we want to integrate with respect to y, we need to get this x squared in terms of y. So that's going to be step 1. So what I might do is maybe just over to the side here. Let's just go back to our original equation or curve that we're concerned with. Y is equal to 1 on root 1 minus x squared. Root 1 minus x squared. Now we want to rearrange for x squared. Now the good news is there's already x squared, so that won't be too hard. So let's just square both sides. So we'd get y squared equals 1 on 1 minus x squared. I'll bring the 1 minus x squared up and the y squared down. So 1 minus x squared equals 1 on y squared. and then I'll bring the x squared over and the 1 on y squared, and then just switch them, and we'd end up with x squared equals 1 minus 1 on y squared. So that's essentially what we want to integrate with respect to y. So I'll just write that out. So we can write these integrals as, I'll bring the pi on 4 out as a constant. The integral from 0 to 2 on root 3 of just 1 dy minus pi times the integral, so I've just brought that pi out, between 1 and 2 on root 3. And now for x squared, I'm just going to put 1 minus 1 on y squared dy. And thankfully, neither of these integrals are particularly hard to integrate. I think that's, in my experience, typically the case with extension 1 or 3 unit. Most of the time they'll be nice enough to kind of, I guess, test really your understanding of the technique of slices, but kind of give you curves that shouldn't be too hard to integrate. Maybe if it's going to be like the final question on the HSC, they might throw in a hard one. But it's typically in the extension 2 where they'll really kind of double this up with tougher integrals. So they're testing both your understanding of volume of revolution and also giving you quite relatively difficult things to integrate. But in this case, thankfully, it's not too bad. So if I just start to evaluate this, we'll have our pi on 4. The integral of 1 with respect to y will just get us y. And that's between 0 and 2 on root 3 minus pi. And then we're integrating 1 again, so that's just y. The minus 1 on y squared we could think of as minus y to the negative 2. And so if we use our basic integration rule of adding 1 to the exponent and dividing by the new exponent, we'd get minus y to the negative 1 on negative 1. That means the minus and minus would become a plus, and we'd end up with y to the negative 1, which we could just write as 1 on y. So hopefully you've followed that. I've kind of just done all that mentally in my head, but I think it's simple enough that hopefully you don't need to see the full working. And our boundaries are between 1 and 2 on root 3. Alright, so now we really just need to kind of throw in the values and simplify. So we'll get pi on 4 times 2 on root 3 minus 0 minus pi. And here we'll do the 2 on root 3 first, so we'll get 2 on root 3 plus, and here it's 1 over, so we'd get root 3 on 2 minus, and then I'll just put this in brackets, we'd have 1 plus 1 on 1 is 1. Alright, so what I might do is just kind of rationalize some denominators to kind of help with the simplification. So here the 2 and the 4 would simplify to pi on 2 root 3, but I'll multiply that by root 3 on root 3, and that would be, we'd get root 3 pi on 2 times 3, which would be 6. So we get root 3 pi on 6 for this here, minus pi, and maybe I'll just keep these brackets, and we'll get 2 root 3 on 3 for this. I've just rationalized the denominator there by multiplying by root 3 on root 3, plus root 3 on 2 minus 2. So we'll have, maybe I'll leave this and I'll kind of factor out the pi in a later step. So we'll go root 3 pi on 6 minus pi, and what I might do is get a common denominator for these, which will be 6, which I think is going to make things quite neat. So to get this on 6, I want to multiply top and bottom by 2, so we'll get 4 root 3 on 6 plus, and here I want to multiply top and bottom by 3, so 3 root 3 on 6 minus 2. So that's going to be, and here I might multiply out the pi as I bring these together. So we get root 3 pi on 6 minus, now the 4 root 3 plus 3 root 3 will be 7 root 3 on 6. So 7 root 3 on 6 times the pi. And then multiplying the minus pi through here, the minuses will become a plus, so plus 2 pi. So that's going to be 2 pi, and then we'll get 1 minus 7 would be minus 6 root 3 pi on 6. 6's will cancel, and that then gives us this kind of 2 pi minus root 3 pi, or if I just factor out the pi, we get 2 minus root 3 pi units cubed. And that's the answer in kind of exact form. If you wanted to, or if you were asked to, you could then just pull out the calculator, and we do 2 minus the square root of 3 times pi, and you get I'll just write it all out, but you'd probably be told what to round to, but we'll just write 84178 72145 and so on, and again units cubed. So we're not actually told units in these questions, and that's quite typical, so we just keep it in the generic units cubed. Panic boom! So there you have it. That's how you do that volume of revolution question. So I think kind of reflecting back on that, relatively hard in that you really need to understand what's going on in terms of the shaded area that we're asked to rotate. The key to this is understanding, well, that's going to involve two integrals. One, to rotate this whole rectangle around, and then two, to rotate just this bit with the curve and then take the difference. I think once you've got your head around that, and you understand the basic technique of you're essentially getting slices that are cylinders, and you understand the volume of a cylinder, or the volume of any prism really is the area of the face times the height. Just putting all that knowledge together, and then understanding that you're summing it you're summing all these slices as the width of the slice gets smaller and smaller, and you're doing it within a range. And that, if you think back to the very definition of what an integral is, that kind of gets you in integration territory. And then ultimately the integration was fairly straightforward. We just had to see the link that we had to get x squared in terms of y, but thankfully that was easy enough. So hopefully you're able to follow along with that. If you found that explanation helpful, please be sure to give the video a like. And if you're someone who wants to keep their finger on the pulse with the kinds of questions other students are struggling with, please be sure to subscribe to my channel so that you can stay in the loop. Alright, tick boom.